Hello and welcome back. This is section 6, and this is a section about writing polynomials from complex roots. Okay, just to go back, what we know about complex roots, when we talk about the word complex, this includes the real and imaginary number system. Okay, so the reason why they did that is because we will be dealing with real number solutions, but we'll also be dealing with imaginary numbered solutions. Okay, and roots, remember that word means a solution to a polynomial. Okay, so a solution to a polynomial. All right, another way of saying that is so that's one way of saying it. Another way of saying a root is a zero of a polynomial. Another way of saying that is an x-intercept. Okay, x-intercept. And so those are what we're talking about is, and what we're doing is we're taking the x-intercepts, okay, or the zeros, or what we call a solution to a polynomial, and we're going to be able to write polynomial functions based off of that. Okay, so let's take a look. We want to write a polynomials as products of factors. So we want to write a polynomial equation with the following roots. So what this tells me, I have x equals -3 and I have x equals 7. Okay, so I'm going to write out each of these separately. X equals -3, and down here I'm going to write x is equal to 7. Okay. Now what I want to do is talk about how that these are solutions. These are answers. Okay. These are what we try to find when we're talking about find the solutions of a polynomial. But we want to take the solutions and write the polynomial. So we want to take these, and in this they are solutions. Okay. Let's call them roots for now. Okay. Okay. And then what I want to do is I want to turn those roots and turn them into factors. I'm going to change colors here for that. Okay, and so if I were to take these and turn these into factors, what I would do is I would put all the numbers and all the variables on one side and set it equal to 0. Okay, so what I'm going to do here is I'm going to add 3 to both sides, add 3. So what we get here is we get that x plus 3 is equal to 0. This is my factor. Okay, so same thing over here. I would subtract 7 from both sides, and that would lead me to then having x minus 7 equal to 0. Okay, these are factors. All right. Now what I want to do is I want to turn it into a polynomial. Okay, so if I take those factors and then I turn it into a polynomial, okay, and I'm just going to call that f of x. Okay, I'm going to let f of x be the polynomial. And what I'm going to do is multiply my two factors together. Okay, and I'm just going to take x plus 3, and I'm going to multiply it by x minus 7. Okay, and so this is done. Okay, what we've done, and that's pretty much it. It's pretty simple. We could multiply this out, and we could say, all right, well, f of x is x squared plus 3x minus 7x minus 21, and I'm just, multiplying it out. And we combine our like terms here in the middle, so we could say that f of x is equal to x squared minus 4x minus 21. Okay, so when what we have here, we have our polynomial, and then we have the solutions. Okay, so given the solutions, write the polynomial. Okay, what we were doing before was we were taking the polynomial and we were finding the solution, so we're going backwards. All right, so but there's a little bit of a discrepancy here. Let's say that we have the roots -5 and -1. Okay, and just to clarify, what this means is that we have those points on our x-intercepts of -5 and +1. Okay, now we can have a various number of solutions or number of polynomials here. Okay, so what we have to consider is the fact that if I were just to take my roots, okay, and turn them into factors and write my polynomial, okay, I get this nice, orange curve here. However, we could have some sort of multiplier out here, okay, that changes the graph, changes the minimum point, but it keeps the same or x-intercepts keeps the same roots. Okay, so we will have to take a look at that and use that later on. Okay, and same thing with like the multiplicity of roots. Okay, you know what I have here is I have the roots of -5 and 1. Okay, and the standard function that we would get from that is we would get this function here. F of x is equal to x plus 5 times x minus 1, that same, parabola that we got. But what if we had a multiplicity of 2 on the root of -5, okay? Which then turns this into a degree 3 polynomial, all right? And what happens is at positive 5, or at -5, notice that we don't, we have an intercept, but we don't go through that intercept, all right? And the same thing if we multiply x minus 1, that factor out a couple times, we end up getting, a different function, okay? So there are a couple things that we have to, account for when we're doing this, all right? All right, let's take a look at the irrational root theorem, okay? It says that, that if a number, a plus the square root of b, is a root of a polynomial equation, where a and b are rational numbers and the square root of b is an irrational number, then we know that a minus the square root of b is also a root, okay? So this is the same thing as the complex, similar to the complex conjugate theorem from the last section, okay? So this is similar to the complex conjugate theorem. Okay, so if you get some sort of irrational number as a root, know that you're going to get both a positive and negative one out of it. Okay, so let's go ahead and let's take a look at the next page.